Hello, my name's John Ludlam, and I'll be giving our talk entitled A Multiverse of Glorious Documentation, written by Lucas Bluvenage and myself. Those of you that were here last year may remember I gave a talk about ODoc entitled The Final Piece of the Documentation Puzzle. Now you might notice that I'm back with more documentation work, so you might reasonably think that perhaps last year's title was maybe a little premature. The difference this year, however, is that I want to expand our scope. We were less ambitious last year. We only looked at documenting a single library. This year, I want to document every single library I've ever seen, and all the libraries I've never seen too, and even every version of all of those libraries. And I'm going to tell you how to combine all of those library documents into not just a glorious universe of documents, but an entire multiverse. Let's go. As usual, we start with the goals. We're looking at the OPAM repository, and we want to produce documentation for each of the versions of the packages in there. This amounts to just short of 20,000 versions as of today. A lot of packages, to be sure, but not insurmountable. In fact, we actually end up documenting a few more than that, and I'll discuss the reasons why this is the case in a bit. Additionally, we'd like this to be an automated process, so we can just let it get on with things and not worry about it. I don't particularly want to have to schedule a weekly update the docs slot into my Monday mornings. Even better, let's have it such that any time a new package or version is merged into opamrepository.git, we'll build docs for it. And while we're at it, let's have it quickly. Let's aim for about 10 minutes and see how we do. And if the server we're running on it dies a horrible death, we need to be able to start it all up again without too many tears. And finally, let's make it a useful basis for future work. Okay, so now we know what we want. How are we going to do it? Well, no surprises here given my talk last year. We're going to use ODoc. It's the only tool in the game, really. The trouble is that the way ODoc works is that it requires a consistent set of packages that are all co-installable, or more accurately, co-typable. To understand why, see my talk from last year. So that rules out having more than one version of a package. What we're going to do then is build the documents separately into some carefully defined file tree, and then union the trees together into one set of docs. Happily, ODoc 2.0 supports rendering HTML into an arbitrary file structure, so we're good to go. Our next decision is therefore exactly what file layout will we use. Well, the most obvious answer is just to stick the HTML docs into a file structure based on the package name and version. Is this efficient? Sadly, no, it's not. The fact is that the interface exposed by a package is dependent not only on the package itself, but on the exact versions of its dependencies. Consider, for example, a package that exposes a set created from the functor in the standard library, specialized in this case so that the type T is equal to myType. In this signature, the function filterMap has only been included since OCaml 4.11, so if you build this exact package against 4.10, it would not contain that value. Obviously, the standard library is not unique in this, so it's entirely possible for the interface of a package to change if you change the version of any of its dependencies. Consequently, in order for the cross-referencing to be exact and correct, we need to identify a particular set of docs for a package not just by the package name and version, but by the triple of package name, package version, and universe ID, the last of which we define as a hash dependent on the package's version's dependencies. The next question, can we get away with only ever compiling each version of each package against one set of dependencies? It would be convenient, but this turns out not to be possible. Take the example of findlib. Virtually all packages depend upon findlib, and with no constraint, meaning OPAM will pick the latest compatible version. However, many packages have constraints on the version of OCaml, so we end up compiling the latest version of findlib against many different versions of the compiler. Consequently, for some packages, we necessarily need to produce documentation for the same version for each different universe in which it's needed. Since these may be different, we need to ensure that these are put in different paths. So the most obvious way to do this is to use the universe ID as part of the path. So something like /packages /universe ID /package name /package version. While this scheme is correct, it doesn't lead to particularly discoverable, pleasant, or easy to remember URLs. To fix this, what we do is pick one particular universe to be the representative for each version of each package. I'll describe later the exact mechanism we use for this at the moment, But the important thing is that this gives us a way to have a nice discoverable and easy to use URL for each package version, while retaining the correctness that every link can be guaranteed to go to the destination that the package was actually compiled against. We call the chosen representative universe the blessed universe. We use OCurrent to build an incremental pipeline to build the docs. So this is the same system that's being used for CI systems such as OCaml CI. It's designed to watch Git repositories for updates and respond by submitting jobs to a cluster for execution. It's got some really nice caching built in that works really well, though it's not quite capable enough today to match our needs. So we've built a bit more of a stateful pipeline. Not only that, but since the artifacts we work with are quite large, we store them on an external file system, and that in itself is a stateful part. So we really have two states to keep in sync. OCurrent encourages incremental builds, so that even when the build graph changes, for example, when a new package or version is committed into OPAM repository, it only rebuilds the new artifacts required. It does this by defining a key value pair for each step in the build process. It then memoizes the results, so if it's already calculated the value associated with the key or keys, it just returns the previous calculated result. Let's take a look in more detail at some of these individual parts. The solver's job is, for each package and version we're tracking, to run an OPAM solver to find the precise set of packages required to install it. The inputs, the key, is the commit hash of OPAM repository and the list of the packages we're interested in, and the resulting value is the list of solutions. We do keep some additional state, the list of previously solved packages, so that when the input changes, which is most often a new commit on OPAM repository, we can decide whether our previous solutions are still valid. Right now, if we have a cached version, we'll always reuse it, but we'll likely adjust this in the future. There are a variety of circumstances under which we'll want to resolve. For example, we'll almost certainly want to resolve for everything when a new compiler is released, as in many cases the solutions will change to use this newly released compiler. Possibly we'll also want to resolve just on a regular cadence to ensure our solutions are reasonably up to date. We do not insist on installing the optional dependencies where they exist, as it's perfectly possible for optional dependencies to be mutually exclusive, or for some broken packages for the optional dependencies to cause the build to fail. To some extent, we do make up for this in the blessing step. Once we've got a solution, the next step is to install it. The pipeline takes care of choosing a base Docker image to use with an appropriate compiler version, then invokes OPAM to install the packages. It runs the tool voodoo prep to find the files within the OPAM folder that are necessary to produce the docs. Mostly this is the CMTI, CMT and CMI files that ODoc requires, but we also pull out a few more files. Any package docs installed, Dune package files for a bit of metadata, and some info from some of the CMA files if Dune package doesn't exist. These files are then tarred up and pushed to the external file system and the hash calculated. The hash is the value of this part of the pipeline. When we've got the complete builds, we can choose which universes to be blessed. We do this by picking a universe with the most dependencies. Doing this means that when we've got a successful build with some of a package's optional dependencies, which occurs when a dependent package has a non-optional dependency, then the blessed universe will have the docs for the package's optional libraries. When a tiebreaker is needed, we simply count the number of dependent universes and choose the universe that's included in more of our other universes. Once we have the artifacts extracted from the OPAM directory, the next step is to perform the ODoc compile and link steps. These are roughly analogous to the usual compile and link steps. To compile the docs, we require the results of compiling all of the dependencies, hence this forms part of the key of this step. Furthermore, this is the first step in which ODoc is actually required, and since we're using an unreleased version of ODoc right now, we track the commit ID here too. For more details on this step, see last year's talk again. The result of this is the linked version of the docs that can then be converted to a variety of output formats. Here's a section of the compilation pipeline showing the pipeline stages in this compilation step following the dependency ordering of the packages. So you can see LWT depending on OCaml syntax shims and Dune configurator and mmap and so forth, and then subsequently cstruct LWT depending on that, and also cstruct and so on. The separation of the HTML generation step is done largely to ensure that we can rerun this quickly as the desired output changes. To rerun this step over all universes only takes about 90 minutes at the moment. We have a slightly altered HTML generation step than ODoc usually has, which has allowed the integration of the docs into other sites easily, in particular, of course, v3.ocaml.org. This HTML generation tool is currently being prototyped in the Voodoo suite of tools, but it's likely we'll fold it back into ODoc once we decide on the most useful output format. As with all live systems, we need to have a policy on how updates are handled. In general, the updates are either breaking changes or non-breaking changes. As an example of a non-breaking change, we might have a new package put into OPAM repository. This could be done simply by inserting the new set of HTML files into the appropriate place in the unioned file system. A breaking change is anything that might cause links to break or the downstream consumers to break. For example, if we change the layout of the metadata consumed by the v3.ocaml.org server, we might wish to do that atomically across all packages rather than just incrementally. For these sorts of changes, we have what we call an epoch symlink on the server. When the build is completely finished, we simply flip the symlink and atomically switch from one set of metadata to the new set. Some stats on where we currently are. We produce about 50 gigs of HTML files in total. This is across about 3,300 packages and about 17,400 versions. And about 2K are actual installation failures, so where the build has failed at the time we try and do the OPAM install. We have 18,600 versions living in parallel universes and producing 3.3 million documentation pages. The package that has the largest number of parallel universes is actually logs, which occurs when logs 0.7.0, which occurs in 209 different universes. The total build time across the OCaml Labs cluster, when the cluster is not being particularly used, is about 6 hours. So it doesn't take a huge amount of time, but we have quite a lot of machines there. We have plenty of work left to do. As I mentioned before, we've set up the pipeline to store its artifacts externally, and this is done in a fairly naive way, and there are plenty of opportunities to improve this. Additionally, or alternatively, we might invest in embedding the idea of a data pipeline more directly in OCurrent. We've already got a public API of sorts in place where the documentation generated by the pipeline can be consumed by the v3.ocaml.org server and rendered nicely as part of the new OCaml website. But it would be interesting to think about more other uses of this. For example, we might want to embed the output in the Visual Studio Code plugin in some form, or we might be able to use the data we're generating in alternative ways. For example, some sort of search. We've not done a lot yet on comparing the documentation in different universes. While it's certainly theoretically different, it would be really useful and informative to understand how different it actually can be in practice. And while we're considering comparing the output, it would also be really useful to be able to show the diffs between different versions of a package. Although since they may be compiled against different dependencies, we'd again need to carefully consider what the source of the differences is. In short, there remains much work to be done. So, thank you very much to our colleagues at OCaml Labs and at Teredes, in particular Jules Aguillon, Lubega Simon, Patrick Ferris and Thibaut Mathieu, to the rest of the ODoc team and to Jane Street for their financial support. And thank you all for your attention.